Hello everyone, today I'll be explaining to you three things: series resistors and voltage division, parallel resistors and current division, and supernodes. So now, starting from series resistor and voltage division, we can consider two resistors R1 and R2 connected in a series, just like in this figure. Since they are in series, the same current I will flow through both of them. Now we apply Ohm's law to the resistor, we obtain V is equal to IR. Now second, if we apply KVL to the loop, which is across voltage law, and we have to move in the clockwise direction, we will get this equation moving. See, we can see that in the circuit. If we move into the clockwise direction, we will have first we will have minus V, then positive V2 1, and then positive V2. Now we know that KVL suggests that all voltages, sum of all voltages in a loop, closed loop, is equal to 0. So now we have to put it equal to 0. Combining the both equations, we will get a generalized equation for current, which is I is equal to V over R1 plus R2. Now we can see here that the voltage the resistors can be replaced by an equivalent resistance. Basically, an equivalent resistance is the sum of all the resistances present in the circuit, that equals to equivalent resistance. Like this, the equivalent resistance of any number of circuit resistors connected to the series is the sum of the individual resistance. Exactly what I just explained. It is generally denoted like this for n number of resistors in series. Now we know that voltage across each resistor will be V1 is equal to R1 over R1 plus R2 V. And now we need by looking at this equation, we can see that the voltage drop and the resistance are in direct proportion to each other. That is, if one thing is increasing, if one thing is larger, the other one will also be larger. So it's just that the larger the resistance will be, the larger the voltage drop will also be. This is called the principle of voltage division, which is represented by Vn is equal to Rn over R1 plus R2, and so on to Rn for n number of resistances. Okay, next here is a visual representation of the circuits in which we have applied the equivalence resistance. Like in the first circuit we have two resistances. Now in the second circuit we have just put one equivalent, which is equal to the two in the first circuit. Now next we move on to parallel resistors and current division. We will do it in the same way. We have to consider two resistors R1 and R2, which are connected in a parallel, like shown in the figure below. Therefore, as they are connected in parallel, they will have the same voltage. That is an unknown fact. Now, from Ohm's law, we already know that V is equal to IR, and then to get the value of current, we have to switch it to I is equal to V over R. Now, if we apply the KCL at a node, KCL at node A, it gives a total current I, as we can see that both currents are going into the node. So I will become equal to I1 plus I2. Now we combine the both equations like we did in the series, we'll get this equation. Now in parallel resistance and in parallel resistors, we can also put an equivalent resistance, but in parallel resistance, it is the equivalent resistance slightly changed, because it is not exactly the sum of all the resistances, but instead it has to be it is equal to the equivalence resistance is equal to the product of the two resistances divided by the sum of the two resistances. Now, but for n resistance in parallel, then it will be just reciprocals going to the nth resistor. Next we have, we know the formula of current. We apply it in the equivalence resistance, then we'll get I1 is equal to R2 I over R1 plus R2, and the same in the next one for I2. Now we have to see that the total current I is shared by the resistance in inverse proportion. That is, uh, increase in the one will cause decrease in the other. This is known as the principle of current division, and it is also known as current divider. Now we can see that Same as we saw in the resistors, series resistors, that the two resistors here R1 and R2 are replaced by the same replaced by one resistance, which is known as the equivalence resistance.
So now let's discuss an example. Find equivalent resistance for the circuit shown. You can see that this is a circuit given to us that has many resistors. Some of them are connected in series, some of them are in parallel. Like, it is quite mess. What we need to do is we need to find a single resistor that we can replace this whole circuit with. So that will be equal to equivalent resistance. So what we need to do is we need to find, first step is to analyze the circuit and determine that which two resistors we need to solve in order to simplify the circuit. According to my observation, we can simply solve these two resistors and our circuit will be more simplified. So by seeing these two resistors, we can see that these two resistors are connected in parallel. So we need to apply the formula of 1 over R1 plus 1 over R2 whole inverse. So what 1 over 6 plus 1 over 3 whole inverse will give us answer of 2. So we can replace these two resistors with a single resistor of 2 ohms. Now let's see, we are going to replace these two resistors with a single resistor of 2 ohms. There you go. So as you can see that our circuit is more simplified than that of before. So we can simply add these two resistors as they both are connected in series. So in series, the formula is quite simple. In series, you just simply add up the values. So 2 plus 2 will be equal to 4. Now we can replace these two resistors with a single resistor of 4 ohms. So we did that, and now what we are going to do is we are going to add these two resistors, and by seeing these two resistors we know that these two are connected in series. So we are going to simply add them up. So 5 plus 1 will give us 6. So we can replace these two resistors with a single resistor of 6 ohms. Now our circuit is far more simplified than the initial one. So we can just simply simplify these two resistors, and as they both are connected in parallel, so we are going to apply the formula 1 over R1 plus 1 over R2 whole inverse. So this should give us 2.4 ohms. This means that we can replace these two resistors with a single resistor of 2.4 ohms. Now our circuit is more simplified and we can see that these three resistors are connected in series. So we are just simply going to add them up. 8 plus 4 will give us 12, and 12 plus 2.4 will give us 14.4 ohms. So that means that we can replace these three resistors with a single resistor of 14.4 ohms. So this is our final answer. This means that the whole circuit could be replaced by a single resistor of 14.4 ohms. That was an example. Now we are going to talk about circuit analysis. So what is circuit analysis? Circuit analysis is divided into two parts. Number one, that is nodal analysis. What is nodal analysis? It is based on a systematic application of Kirchhoff's current law, or KCL. What is KCL? KCL states that the amount of current entering a circuit is equal to the amount of current leaving the circuit. So let's visualize this circuit. Let's say this is a current source of 10 amperes and it is connected to a circuit that has two resistors that are connected in parallel. Okay, so we are going to name this resistor R1 and this resistor R2. So when we can see this circuit, we know that the 10 ampere current will flow in this direction. And when the 10 ampere current is going through this node right over here, it will split into two parts. Half, or like some amount of current, will go through the resistor R1 and the rest will go through R2. So we can name them as I1 and I2. What KCL states is that the amount of current entering a circuit is equal to the amount of current leaving the circuit. So we can apply KCL at this node and we can derive an equation that will give us that will say that, let's say 10 ampere current is entering, so we can write it as 10, and the amount of current is equal to the amount of current entering a circuit is equal to the amount of current leaving the circuit. So 10 ampere current is entering the circuit, and the current that is leaving the circuit is I1 and I2. So we can write it as 10 is equal to I1 plus I2. So this equation is derived using KCL. This is what KCL states. Now, in nodal analysis, there are two types of circuit: nodal analysis without voltage sources and nodal analysis with voltage sources. We will discuss these two later on. The second type of circuit analysis is mesh analysis. It is based on a systematic application of Kirchhoff's voltage law, or KVL. Okay, so what is KVL? Let's visualize this. Let's say there is a voltage source of 10 volts. This will be the positive terminal of the voltage source. This will be the negative terminal. So there are two resistors that are connected in series, and we will name the voltage across the first resistor will be equal to V1, and the voltage across the second resistor will be equal to V2. Now we can give them signs as well. This will be positive terminal, this will be negative terminal, this will be positive terminal, and this will be negative terminal. So what KVL says is that we need to move in anti-clockwise direction and just simply use the first sign that is in the way. Let's for example, KVL will say that let's move in anti-clockwise direction. When I'm moving in anti-clockwise direction, the first sign that I came across is this negative sign. So I can write it as negative 10. Now I went through this, and now I'm going towards V1. The first sign is positive, so I can write plus V1. And the third sign that I came across is again positive. I can write it as plus V2 equals to 0. So this equation is derived using KVL. This is Kirchhoff's voltage law. So now let's take a look at nodal analysis. So in nodal analysis, we are interested in finding the node voltages. So there are 3 steps to determine the node voltages. The first step is to select a node as a reference node. You need to analyze the circuit and find a node or select a node as a reference node. And you need to assign the voltages V1, V2, and so on with respect to the reference node to the remaining nodes. The second step is to apply KCL to all non-reference nodes. And the second part of the second step is to apply Ohm's law in order to find the current. And the third step is to simultaneously solve the obtained equations. So first, let's talk about the reference node. The reference node is commonly called the ground since it is assumed to have zero potential, or voltage over the reference node is 0. Reference node is indicated by these 3 symbols, and the most common one is this one, which is the ground. So now let us see an example. This is a circuit that we need to find the voltages across the node 1 and node 2. So remember, the step 1 was to assign a reference node. So we can assign the node 0 as a reference node, and the voltage across node 0 will be 0 volts. Now we are done with the first step. Now let's move on towards the second step. Okay, so the second step was to apply KCL to all the non-reference nodes. So first, let's look at node 1. So what actually is happening at node 1? The current capital I1 is entering the node 1, and the current capital I2, small I2, and small I1 are leaving the circuit, as you can see from this visualization. So the capital I1 current spreads into 3 parts, that is capital I2, small I2, and small I1. So now let's apply KCL at node 1. So what you remember, let's recall that what KCL states that the amount of current entering the circuit is equal to the amount of current leaving the circuit. So capital I1 is entering the circuit, so we can write it as capital I1, and the current that is leaving the circuit is capital I2, and small I1. So we can write it as I1 is equal to capital I2 plus small I1 plus small I2. So this equation is derived from KCL. At node 1, we applied KCL and we got this equation as a result. Now let's see what happens at node 2. Let's see what is happening at node 2. Node 2 is right over here. So now let's visualize that which current is entering node 2 and which current is leaving node 2. So you can see that capital I2 and small I2 are entering the node and small I3 is leaving the node. So let's apply KCL. Capital I2 plus small I2 will be equal to I3. So we derived this equation using KCL at node 2. So now we got this equation and this equation using KCL at node 1 and node 2 respectively. Now we were done with the step 1 and we were done with the first part of step 2. Now let's look at the second part of step 2. Apply Ohm's law to express the unknown currents I1, I2 and I3 in terms of node voltages. So according to the passive sign convention, current flows from a higher potential to a lower potential in a resistor. So the nodes were across a resistor. So we can express this principle as I will be equal to the higher potential minus the lower potential divided by the resistor. So let's see how this thing will apply in our circuit. This was our circuit. Now let's see that what will be the value of I1. Okay, so I1 is flowing from V1 to 0. This was our reference node, so it's the voltage across the reference node was 0. So I1 is flowing from V1 to 0. So we can use this equation and write the value of I1 as higher potential minus lower potential. What is the higher potential from V1 to 0? Higher potential is V1. So we can write V1 minus lower potential. What is the value of lower potential? 0. We can write I1 as V1 minus 0 divided by the resistor. Which resistor is between V1 and 0? That is capital R1. So we are going to write R1. So I1 can be expressed with the term V1 over R1. Now we are going to do the same thing for I2 and I3. Let's see. Okay, so what will be the value of I2? I2 is flowing from V1 towards V2. So we are going to use this formula. Higher potential is V1, lower potential is V2. So V1 minus V2 divided by the resistor, that is R2. Same thing for I3. I3 is flowing from V2 towards the ground. So we can write I3 as V2 minus 0 divided by R3, or simply we can write it as V2 over R3. These three equations are derived using Ohm's law. And one more thing to keep in mind, what this G stands for, this G is conductance. As G was equal to 1 over R, and you can see that 1 over R is in everything, like 1 over R2, 1 over R1, 1 over R3. So we can simply replace them, like for example, when there is R1 resistor, we can simply replace them by G1. So these three equations are derived using this formula. G is for conductance. So from step 1, we have this equation and this equation. These two equations were derived using KCL. From step 2, we found the values of I1, I2 and I3. Now what we need to do is we need to substitute the value of I1, I2 and I3 into the first two equations. So we can simply substitute the values and get these two equations respectively. So I1, small I1 will be replaced by V1 over R1, small I2 will be replaced by V1 minus V2 over R2 and so on. So we have these two equations, or you can also represent these two equations in terms of conductance if you don't know the resistance. Okay, so now we are going to move on step 3. In step 3, we know that we have these two equations And we can solve them by using substitution method, elimination method, Cramer's rule, and matrix inversion. Now, this example didn't had any values, only the variables were involved, so we can simply find the values of V1 and V2 using these four methods. But in some other cases, there will be some values, so we need to simply use the elimination method or the substitution method to find the values of V1 and V2. Now, let's look at an example with some real values in it. So now we have a circuit that has 5 ampere current flowing in this direction and 10 ampere current flowing in this direction. Just remember the three steps. Step 1 was to analyze the circuit and determine a reference node. So we can select this point as our reference node. Here the voltage will be 0 and assign V1 and V2 with respect to this source. So we can state this node as V1 and this node as V2. We need to find voltages across these two nodes. Now let's move on to step 2 and apply KCL at node 1 and node 2. So now we are going to analyze that how current is flowing through node 1. Okay, so now let's visualize this. So 5 ampere current is flowing or is entering in V1 and I2 and I3 is leaving. So we can apply KCL at node 1 and we can write it as 5 is equal to I2 plus I3. And now we can apply Ohm's law. So we know that I2 is equal to higher potential minus lower potential. I2 is flowing from V1 to V2, so we can write it as V1 minus V2 over 4. And similarly, I3 will be given by V1 over 2. So we can substitute these values and find the final equation as these. That is 3V1 minus V2 equals to 20. So we applied KCL at node 1 and we simplified the equation we got after applying Ohm's law, and now this is our final equation for node 1. We applied KCL and got this equation from node 1. Let's visualize how current is flowing through node 2. So I2 and I4 are entering the node and I5 and I1 is leaving the node. The value of I4 is 10 amperes because it is flowing from a source of 10 amperes, and the value of I1 is 5 amperes because it is going back towards the source. So it should be 5 amperes. Now, applying KCL at node 2, we know that I2 and I4 are entering the circuit and I4 has a value of 10 amperes. And I5 and I1 is leaving the circuit and I1 has a value of 5 amperes. So we can write it as small I2 plus 10 is equal to 5 plus I5. And if you don't want to substitute the value, you can simply write it as I2 plus I4 is equal to I1 plus I5. Now we are just going to apply Ohm's law, that was higher potential minus lower potential. So I2 will become V1 minus V2 over 4 and I5 will become V2 over 6 and I1 and I4's value are already given. So now let's simplify this term and we have this equation from node 2. We had 3V1 minus V2 equals to 20, the equation 1 from node 1, and we have minus 3V1 plus 5V2 equals to 60 as equation 2 from node 2. We need to just simply substitute, or we can, as 3V1 and 3V1 are same, we can just simply add them up and this 3V1 will cancel out and we are left with this equation, and this equation can be further simplified to find the value of V2, that is 20 volts. And we can simply substitute in any of these equations and find the value of V1, that is 13.33 V.
Okay, so next we have a supernode. What exactly is a supernode? A supernode is formed by enclosing a voltage source connected between two non-reference nodes and any elements connected in parallel with it. See here in the circuit in the figure, node 2 and node 3 form a supernode. That is because they are enclosing a voltage source, and they are two non-reference nodes, which are also in parallel. Now we can analyze the circuit with supernodes using the same three steps that Abdullah has previously mentioned, except that supernodes are treated a little bit differently. An essential component of nodal analysis is applying KCL, which requires knowing the current through each element. There is no way of knowing that the current through the voltage source in advance. However, but still KCL must be satisfied at supernode like any other node. Okay, so now uh, at the supernode, we know that two currents are entering the node and two currents are leaving the node. I1 and I4 are entering while I2 and I3 are leaving. Uh, if we apply the KVL, we'll know that sum of all the voltage is equal to 0. Now solving the equation, we will get I1 plus I4 is equal to I2 plus I3. As we already know the value of resistances present in this circuit, we can directly replace it with their values in the formula we derived above. Now, when we apply Kirchhoff's voltage law to the supernode, we know that we follow this loop clockwise. Now, moving in clockwise direction, we'll see that the V2 is negative. Then we get to the 5 voltage source, and then we move on to the positive V3, all of which should be equal to 0. Now, to get the voltages value, we can arrange it as V2 minus V3 is equal to 5. Okay, next, yeah, we knew that V1 was equal to 10 volts from here. Here you can see the first voltage source is 10 volts. Now just put the voltages in, we put the values and calculate the answers, and we'll get the V2 and V3 as well.
Properties of supernode. Note the following properties are of a supernode: that the voltage inside the supernode provides an equation needed to solve the nodal voltages, and a supernode has no voltage of its own, and the supernode requires both KCL and KVL in order to solve the nodes. Now let us look at an example. Um, for this circuit, we need to find the voltages across the node V1 and V2. So remember the three steps. The first step was to select a reference node and assign V1 and V2 in accordance with the reference node. So step 1 is already done. Now let's look at step 2. Okay, so now step 2 was to apply KCL. But if you can see that in normal circumstances, we had to apply KCL at node 1 and KCL at node 2. But as this is a super node, so we will consider this as a single node and we will not apply KCL separately, but we will apply KCL on this single node. So now let's visualize how current is flowing through this node. So 2 ampere current enters the circuit, and small I1 and small I2 and 7 ampere current leaves the circuit. So we can apply KCL at this point and derive an equation that will say that 2 is equal to small I1 plus I2 plus 7. So this equation is derived using KCL. Now we simply apply Ohm's law and derive this equation. I1 will be equal to V1 over 2 and I2 will be equal to V2 over 4, and the value of this is 2 amperes and the last current is 7 amperes. So simply we need to apply Ohm's law and we get this equation. And now we simply need to take LCM and we have this equation. V2 is equal to negative 20 minus 2V1. Now we need to apply KCL over this supernode. Now let's apply KVL. Remember, KVL was in anti-clockwise direction and we noted the first sign that came across. So now let's move in an anti-clockwise direction. So the first sign that we come across is minus V1. The second sign is again minus 2. And the third sign is positive, that is plus V2 is equal to 0. So this equation, this second equation is derived using KVL. Now we have these two equations. So we can these two have V2 same, so we can write it as V1 plus V2 is equal to minus 20 minus 2 VI. So we can simplify and find the value of V1, that is minus 7.33 volts, and find the value of V2, that is minus 5.33 volts. And that's how we do nodal analysis with a voltage source in between. Thank you.